Hey everyone, my name is Paras Chopra, and today I'm with Professor James Evans. He's the director of Knowledge Lab and faculty at Sociology department at University of Chicago. His research uses machine learning and large-scale data to study how collectives think and what they know. By collectives, I mean groups of people like scientists doing science or Wikipedia editors editing Wikipedia. He's interested in knowing how they discover new ideas collectively, how social norms emerge within those communities, and in general, how dynamics impact what they end up doing collectively. Particularly, he's interested in innovation and how institutions within those communities can accelerate or slow down innovation. His research suggests that science is not just an automatic truth machine. Rather, what we end up discovering, what we end up knowing, is determined by how scientists interact with each other. This area of research broadly is called meta science, and that's what we are going to discuss with Professor James Evans today. So thank you, Professor, for your time today.
My pleasure. Thanks for inviting me, Paris.
Fantastic. So I wanted to begin understanding, how did you get interested in studying science and how science happens? This is a relatively unusual area and relatively new one, formalizing and applying machine learning into studying science. What has been your career trajectory that led you to studying this?
Thanks. I've always been interested in ideas, intellectual history, for example, in college, and I would say broadly the way, as an anthropology undergraduate, the way in which milieu and context ends up shaping the questions people ask and the answers that they achieve, even outside of the context of science. And when I was in graduate school at Stanford in the late 1990s, there were a number of high-profile news pieces that, for example, in the Atlantic on the Kept University and the Knowledge Machine and in the Economist, there were concerns about the academy being captured by industrial interests and that shaping its objectivity and the way in which it was thinking about things. At the same time, I was living in Palo Alto, and I was next to companies like Genentech, who had, even though at the time Stanford's biology department, for example, was the strongest, arguably, in the world. Scientists at Genentech, who were exploring a range of diseases and their biological antecedents, were publishing papers that were systematically higher profile and seemed more penetrating than those in the academy. And so I also felt like it was impossible that industry was just dumbed down academic science. And so that led to a dissertation project that really explored the ways in which different kinds of private and public interests and priors by individuals and institutional forces and incentives began to shape ideas. And I must say, even though it might be that not that many at the time studied these things, I would say there's been a really growing movement that we've called the science of science, of scientists from all kinds of backgrounds, physics, ecology, psychology, and elsewhere, who've really applied the kind of full range of their formal and academic imaginations to the problems of how do we make science run better. And so I would say it's really become a growing and exciting community with a number of interesting discoveries, and I think many more on the way. I mean, it really feels like it's leverage. Understanding this allows us to get a little more leverage on both our dollars, but also our efforts and our time in discovering in other places, in physics and epidemiology and places that matter.
Right. I think it's so fascinating that structures and incentives ultimately, there is this wiggle room in how do you design structures and incentives to influence what we ultimately end up knowing, because generally the impression of science is that it just progresses on its own pace and discovers more and more truth over a period of time. But like your research suggests, there is a lot of wiggle room in arranging groups of scientists in a certain way to sort of push things in one direction or another. So I did want to sort of get into this thing of replication crisis. Replication crisis, it emerged in a few fields, and now more and more fields are discovering that many of their findings are actually non-replicable. So I did want to understand from you, my understanding of replication crisis is really from the outside. So what is replication crisis and what's contributing to this phenomena?
Sure. So I would call it more a perceived replication crisis than a replication crisis, in the sense that I don't think that things are replicating worse today than they were 20 or 30 or 40 years ago. I think that this really grew up around a number of concerns which were flagged by some important papers. One by J.P. Unitas in 2005 in PLOS Medicine. It was a simulation study that suggested, based on some simple calculations, so he now is a physician and academic at Stanford, and in 2005, he basically analyzed the structure of, at the time, genetic associations. So these were links between drugs and disease-related genes, and basically kind of calculated how, based on the incentives of scientists within a paper to demonstrate statistical significance, that it was likely that most of the findings that would be presented would be perceived as false if you thought of them as an entire batch. And that really kind of kicked off a series of investigations in genetics and pharmacology, but also in psychology, where I would say they've kind of raged the kind of like the hardest, where people really asked deep and hard questions about the degree to which things in the past that were published by scholars and journals could be replicated independent of the authors that produced those initial papers, outside the context of their initial discovery. And it turns out that many of those discoveries could not be replicated. So only about a third, for example, of the genetic discoveries that were kind of posed and pitched by J.P. Unitas in a big study by Merck ended up being replicated in any meaningful way. In social psychology, especially experiments surrounding priming effects tended to be notoriously fragile to replication. And there are other experiments in other areas that other people have analyzed in experimental economics, in cognitive psychology, which have been more likely to hold up robust to other examinations. But I think the bottom line is just a realization that the literature is not fail-safe, as you say. It's not a truth machine. And some things replicate and some things don't. We can't rely equally upon the past literature. And so I think it's become a crisis in the sense that fields have been taking serious responsibility in some cases and thinking hard about how editorial practices and things they can do as fields could alter confidence in the literature and really the deepening and strengthening of their stocks of knowledge. And so I think they're beautiful things that have come out of that, beautiful considerations. I think there are also some problematic considerations. So vilification, for example, of novel or creative research, which may or may not be able to be replicated. I think there is a place for creative research designs that kind of push possibilities, even if they're not immediately replicable for the imagination of science. So I think that one can go too far. In some cases, things have gone too far. I mean, at the limit, sometimes only very boring experiments occur. Everything must be pre-registered, which means no scientist is authorized to think up a new idea in the context of research. I mean, this would be, I think this would be a really horrible outcome if it became institutionalized. But I think there are many important concerns that have been raised.
I want to just dig on this phrase you used, perceived replication crisis. Why did you use perceived as a modifier. I don't think I fully understood. Why isn't it an actual replication crisis, but a perceived one?
Okay, I guess I just mean that it's not obvious to me that the replication problem, if we're talking about like the likelihood of replication, has gotten worse over the years. So when we think of crisis or like a pandemic, we think like there's this disease and it's here in greater numbers than ever before. And I don't believe that we're having greater numbers of lacking replication than ever before. I think we all of a sudden realized what was true all along, which is that some things are true and some things are true. Some things show up in a context and they don't scale or don't generalize outside that context. And my response is kind of duh. I mean, science is a messy process. I never assumed, for example, that science did, produce consistent, accurate findings. It's so contingent. I'm delighted that it produces as much robust knowledge as it does. I'd like to, if I can, be helpful in figuring out how it could be even more robust.
Right. Yeah. I mean, somehow this sounds even worse, that we were always perhaps in some sort of a replication problem. Then it's a new thing.
Replication deniers. That's right. We're in replication denial, assuming that, at the same time, though, if you were to talk to established scholars, nobody in science thought that all the findings in their field replicated. I mean, that's why people did replication or picked new problems. So I think that I don't even think it really. I think it's like a publicly perceived replication crisis that I think scientists are taking seriously. I think there are some areas, like for example, priming studies in social psychology, which the field does feel differently about. They feel that they are more fragile than they felt before, and so that is a correction, and I think an important correction. So, and I also think that increasingly, and I think this is the important side of the work, increasingly we are getting indicators of, work that's more and less likely to replicate. And those, I think, are allowing us to be much more productive. I think it's, I think the binary black and white, I lose confidence, complete confidence if something isn't 100% true. I see this, for example, surrounding the pandemic in the US, people criticizing Anthony Fauci for at the beginning of the crisis saying that masks weren't important, and then saying masks are important. And then, like he's changing his mind as a result of evidence that is continually coming out. And that's what science is about. It's about a commitment to an unfolding and changing truth, unfolding and changing standards and methods relative to to new and emerging insights. So it's necessarily dynamic, and I think we are. At least I feel like we've learned a lot in the last 15 years since that really wonderful Unitas piece.
This self-correcting nature of science is the best mechanism we've got to approach this mythical truth closer and closer, even though we don't know how far we might be from it. Professor,
I think that's critical. Mythical truth. I mean, I think that the fact that we can appeal to that truth in the context of our disputes is a critical aspect of the culture of science. That is, that's, I would say, broadly universal. Universal in the sense that when people's inquiry is quashed, it's engaged in furtively because people feel bad about it, because they recognize that it's going to go against perceptions of the pursuit of mythical truth. So I think that these aspects of the fantasy of science are absolutely critical aspect of its culture that enables self-correction.
Right. And I think this thing about mythical truth also makes one question, how do truths get established in fields? I was watching one of your lectures, and in that you talk about I think canonization of truths within some fields. So can you talk a little bit about how does that happen? How do some truths become so firmly established that now they're indistinguishable from so-called truth out there?
Well, I think one of the things that is a critical aspect of science, really from the scientific revolution and the late Renaissance, is the fact that individual scientists can't know everything. We have to rely on others to know most of what we know. So I may be able to perform, some little space of studies, but I personally can't perform all the studies involved, and I can't verify all the components and like the tools that I'm using. I have to rely on many others, an industry of others, different industries of others. And so a lot of agreement in science is really about coming to agree. Because we have to rely on others, they have to rely on us, then there's a process by which we kind of calibrate whether we trust them and they trust us. And so what happens in fields oftentimes is sometimes there's like dispositive evidence that we discover, empirically new evidence that changes the mind of a field. In other cases, a field can converge not because of evidence, but because of a series of interlocking mutual agreements where we kind of basically calibrate ourselves until we're kind of looking each other in the eye, and we all assume that a certain thing is true, and we build things on those assumptions, and those things kind of work, which we take as a loose second order verification that these original assumptions that we had were true. And what we see is in sciences, and I've seen this in the social sciences and measured it in the biological sciences, increasingly in the physical sciences, is where there's a lot of communication. So, for example, there are lots of shared authors and shared networks of communication. Then those fields are much more likely to converge to a canonized set of facts as a function of those conversations. And so you'll see that one of the problems, so historically, I would say, in something called meta-analysis, where people study a bunch of studies, for example, that may be done in a drug or a treatment, one of the things that they've been concerned about is, well, what about the outlier? Someone finds that there's this miracle cure, and they measure it as having a massive efficacy, huge effect, and everyone else kind of measures it as not having a large effect, and you average out all those effects. And if that effect from that one study was huge enough, then it can drive up the average, and it can look like it's significant to the whole anyway. And we found that is occasionally a problem, but an even larger problem is where you have people on these teams that are shared. And they're studying the things in the same way, and actually you get more agreement than you would have gotten, even if the effect was true at random. So this is problematic. This is problematic where we come to agree on a finding because your team and my team are sharing the same postdoc who's preparing the materials in the same way and performing precisely the same experiment. And so even though it looks like they're two independent signals of success, they're really one, experiment that's performed basically precisely and fragilely in the same way twice. If some other group independent of our groups, or who'd only read the paper from our groups, had undertaken that experiment, then they would not have found, or they would be much less likely to find the same thing. So, right. So this is, and one thing that we recently, it's a paper that's under review, but we look at as fields grow, that growth ends up inducing a series of conversations, that take place across the field, and there is an explicit canonization of the things on which you build, right? So there's this complete collapse in the diversity of ideas that a field studies as a result of growing quickly. So there are a number of ways in which facts and kind of like canons or canonical papers or ideas become like crystallized within fields and limit their unfolding emergent ability to change over time and to self-correct.
Right. I really liked your differentiation between replicability and robustness, where replicability, like you're saying, you can keep on repeating the same exact experiment infinite number of times, and it would likely replicate in those precise conditions. But robustness is where even if you change conditions a little bit, does the effect persist? And in that sense, your suggestion or your research found out that the more fields grow, the more they get to common protocols, the more replicable their results might be, but the less robust their results might be.
Yeah, which for things that we care about is deeply problematic. I mean, if we're in biomedicine, for example, we don't care that a rat under very precise conditions provided with like a sonic pipette titration of some disease at some particular level was cured, or that, we care that disease, when applied to a human in a variety of clinical conditions, will be cured. We care about robust facts. And so now it's true that occasionally, if we do find an unusual insight that is it's fragile to perturbation, but we can control the environment enough, we can change the world enough to actually make that a stable or robust insight. I think that's less science and more technology. It's critical, it's important. But for most things, we can't change the world to basically fit the fragility of a finding. And we need to focus our minds on robust facts.
So with everyone, the dominant voice being of open science, where you share code, data sets, share basically everything, are you suggesting we need to have more closed science?
Yeah, I am. I'm suggesting that we need, I think there is there's a problem that so people who've been interested in open science from the very beginning, and when I say the very beginning, maybe I'm not going back far enough, but I'm thinking people like Leibniz, in the 17th century. These are, many of these folks were really excited about complete agreement on our concepts. So they argued for this idea of a begriff shift, which later became the basis of modern logic. They wanted everyone to have a singular set of concepts so we could create a machine, that could just kind of create new ideas. They wanted to have, singular sets of shared data to reduce replication needs. And I think that's a deeply misguided effort. I think it's a deeply misguided effort because it misses the fact that for almost everything we care about it applying across different contexts. And much of the discovery happens as definitions of ideas and concepts are changed. And so I think that it's true. It would be deeply problematic if we all agreed and we all produced just one big data set on which we now I should say a correction to that is sometimes there are experiments that are so expensive that we really can only afford one. And in those cases, we just have to recognize that there's a reasonable likelihood that we're wrong. If we can only perform one massive, super high energy physics experiment and get a certain result, now I would say high energy physicists, they take this seriously. And so they spend a ton of time running simulations of the method that they have to see, to figure out, because there's the machines that produce the results are so complicated that no one, that don't fit in some reduced form equation. But nevertheless, those effects are fragile, to be clear. They are. This is, and we just have to, some experiments are thrilling enough that we just have to be willing to be wrong. To be willing to undertake them. And so I think for example, even if in my work I've looked at, for example, the number of different communities, as that number grows, the likelihood of the robustness of those findings, for example, about gene-gene interactions or about drug-gene interactions, dramatically increases, and I mean dramatically. So it's like it multiplies. It's not. I mean, it's so, or is a linear effect. It's a very sizable dose response effect. Unfortunately, that's expensive. It's expensive to have independent data sets and have independent groups, and not to benefit from the supposed synergies of single centers that share everything across them. But those create an epistemic fragility that we need to recognize. We're paying something for that discount.
Right. I mean, while you were talking about high energy physics, I just remembered the story of how gravitational waves were detected, and the team that was there, they didn't even know whether it was like an injected artificial data or the real data. Physicists do take this seriously, but what you're suggesting, if we just have one instance, we should be just slightly suspicious that the finding could be a fluke.
Yeah, I mean, suspicious is I wouldn't call it suspicious. I mean, I'm skeptical of many scientific findings, but I wouldn't call myself a skeptic in the sense that it just means, as if I were to describe myself as a Bayesian reasoner, it just means that I'd be delighted if those things replicated, but in many cases I don't expect them to replicate.
You wouldn't bet your life on it.
No, but that doesn't mean that I'm not interested in it, and that I wouldn't be, I want science to succeed. I actually am a believer in the importance of greater failure in the context of science, because I think one of the things that we see over and over again, and this puts me at odds with many of those who are, study replication, who feel like, hey, we just need to hunker down on the 2 or 3 things that we really know and build slowly from there. And I think that's a strategy if you don't want to fail in science, if you want to discover radical new things. And that's the benefit that I'm banking on, not just the incremental benefit, but the big advances. Then what it means is you just need to increase your budget for failures. And that's difficult for politicians, for example, to fund science, recognizing there'll be higher failure rates. I think this will require a public education process that we celebrate failures, we acknowledge failures. Hiding failures is one of the core reasons, I would say, behind the replication crisis, because people pretend that the things that succeeded were the only things that were attempted, which ends up just screwing up the entire understanding and calculus of our certainty.
Right. I mean, the more I read about this, the more parallels I find between this and how startups innovation happens, where venture capitalists take risk on behalf of entrepreneurs, and we get innovation in the economy essentially because so many entrepreneurs are taking risks, and they're rewarded, and some fraction of them are rewarded. But in science, because the way funding works right now through government agencies, the risk-taking appetite is not there.
Well, I would say it's not just funding. I think it's also just institutional promotion traditions. So I think that, the assumption is that someone has a brand and they're respected and they have this continued, space of work. And talking about failures is uncommon. It's unpopular, and it's just kind of seen as, scientists the assumption is that you're going to undertake a project and it's going to work. And I think if we do that, if we converge to that, then we'll never discover anything meaningfully new. We'll just I'm not saying that won't produce a little more robustness to knowledge that we already have, but it's just not going to take us in fundamentally new directions. We'll need to fail. And I like venture capital. I like entrepreneurship. I like it a lot. And I think the idea, I call it the cartoon of venture capital, where a venture capital fund, funds 20 companies with the expectation that one will succeed, that 19 will fail. and they're going to balance all different kinds of risks and fail in all different kinds of ways in the wide search for the thing that succeeds. And that the entrepreneur, the lean company idea, that the company is constantly pivoting to explore a much wider range of possibilities than it could if it was like committed and stayed on a single path. I love those ideas. But even in practice, those aren't realized. Even though, so for example, in venture capital, even though an individual fund might broaden itself, there's an amazing quantity of follow the leader in venture capital. So a single company, for example, might be funded by 20 or 30 venture capitalists who all so everyone's following one another in that space. And so even though it looks like a single fund is trying to be independent with respect to each of its investments, they're not independent with respect to other venture capital firms, which ends up leading collectively to, I think, a lack of willingness to explore even that entrepreneurial space. So I think we need to fail more all around, and for success. I actually think that that there's too much fear even in venture capital. Which leads to this follow the leader effect.
But thankfully, the profit motive and chasing returns, I think that does create a larger diversity of funders and people who are willing to take a bet even at the completely wacky idea versus what would happen in science.
I agree, or at the very least, I think that idea, is important in venture capital. I'm not sure if I'm in the process of studying it. I'm not sure the degree to which that actually occurs, but I do think the idea, in the same way that the idea of kind of like an unparalleled and untrammeled in pursuit of truth is critical for science. I think that this idea of kind of like exploring every wacky idea is critical for entrepreneurship and venture capital, even though I think that as a society and as systems, we could do better at it.
Right. So you said that it's the lack of risk-taking appetite in science is not just to do with the institutions, but perhaps, not just the funding agencies, but general perception of brand and reputation and so on. So how much, obviously, I think I agree with you, and most people would agree that we need to take more risk collectively. But do you have thoughts on how to push the system towards that? What changes need to happen so we have more breakthrough, more innovative science overall?
Well, again, if we have that, we're also going to have more failure. So I think, how do we sustain more productive failure without, killing the people who undertake it, right? So I think, one of the big risks is if you fail, systematically, at least in our current science environment, you will be culled from the system. You won't get promoted. You can't make your living in science unless you're independently wealthy. Like one of the gentlemen at the beginning of the scientific revolution, and I think we'll need to explore a variety of different kinds of incentives. So there are some direct incentive structures, for example. So I would say the Gates Foundation has attempted this, where they explicitly fund high-risk things. So they frame a target. In their case, often they're practical targets like toilets for the developing world, where we don't have a lot of water, we don't have, so they lay out a constraint, and then it could be that there is no solution, or that there's no solution today that can satisfy that. So that's just an explicitly high risk targeting. And I think we should value things that are valuable, that would be valuable at the end, not just valuable to science. So I think that's one thing. A second thing is group evaluation. So one of the things that made Bell Laboratories, which was attached with the classic AT&T, American Telegraph and Telephone Company, so successful was its commitment to group level evaluation. So you could have departments where you'd have all kinds of people exploring different approaches for transmission of information, or for energy capture, or for whatever it was they were trying to explore, and the entire unit would be rewarded in some ways as a function of the success of anyone in that group. So it really, it really changed the dynamic. People were willing to undertake risks because they knew that they weren't going to die. They weren't going to have to leave the system and be fired if they took a pathway that wasn't successful. And so I think, finding ways to support collectivity's search and valorizing failure as a critical aspect of scientific success and search is going to be absolutely critical. If we don't do that, then we just won't have people undertaking it because the personal cost is too high. Right. And I think some places like the Howard Hughes Medical Foundation is one example. Now, yes, they cherry pick, people who already have shown some signs of success, but then, even though sometimes that success is early and it's short before they begin funding, they provide a sustained commitment to funding with the encouragement to undertake really risky projects. And some colleagues of mine at MIT and at Berkeley have analyzed some of this data and found that those scientists, in fact, do undertake more risky, kind of long-term payout ventures as a result of their undertaking. So I think there are knobs that we can turn that make it possible. I don't think individuals necessarily have an aversion to risk. I think that if we set up incentives that make it possible for them to survive a failure, if we don't, then the only people who undertake failures are the buccaneers of science. And while, I value them and I'm grateful for them, there's not that many of them. Those who are really willing to throw their reputation under the train to kind of find something new. And, that's a rare person. And I don't think we want innovation to be a rare activity.
Yeah. So talking of knobs to increase innovation, I'm not sure if you've studied this or you have an opinion, but I'm going to ask you anyway. You feel, say, young scientists should probably think of doing science in the context of industry or maybe doing a startup of their own where risk-taking appetite is relatively larger versus relying on grants where risk-taking ability right now is not there?
I mean, this is, as you say, it's my personal opinion. I haven't studied this because there's all kinds of confounders. Confounders are other explanations for the same thing. But I would say that anything that increases the ability of an individual to cultivate a risk portfolio of opportunities increases their likelihood to undertake risk in any particular research investment. So, for example, if a young scientist considers or engages in a startup that decreases their need to get a particular finding, which increases the likelihood that they're going to undertake a project that for which their ideas make a difference, right? Not a sure bet, a sure thing. So one of the things that we find in this canonization of facts idea is that a surefire way to get citations is not just to be right, but to publish stuff that's nearby a bunch of other publishers. Okay. So if you publish stuff that's on topics that's like a very crowded area, then that on average is going to maximize your ability to get cited because you're just nearby. Like they have to cite you, to be, and that is a terrible incentive. I mean, that basically means that anyone who leaves the pack and does something original is just going to have a lower expected number of citations on average. And that's totally what we see. And so people don't do that for the most part. So I think when people have a startup, when they have another thing besides the academic job, when they undertake different kinds of risks in different ways that allow them to build a portfolio, even just within science. I encourage my students and postdocs, the only way that you yourself are going to be able to celebrate failure is if you don't have a single project. If you have a single project that has to succeed, then you're going to hold on to it with your cold, dead hands. Like you're gonna squeeze a finding out of that study, whether or not a finding deserves to be squeezed. And so So I think engaging in startups, engaging with industry is an innovation pump to the academy. This I have studied. So it turns out that scientists can sometimes be conservative because there are canonical facts, canonical things that we expect. And if we expect those things, then I can make hypotheses that people will believe are likely to be true. And I'll give you, I can be given money from conservative agencies to support those things. Industry has, because of the profit motive, an interest in things that, if they were true, would be commercially meaningful, independent of their likelihood of being true. So I would say engagement with industry is like an innovation pump to science, because you basically get a set of motives and a set of questions that they want to figure out if they're true, independent of reasons relating to their assurity that they are true. Right? Does that make any sense?
Yeah. I mean, interestingly, this is how many organizations manage their innovation pipeline. I mean, they literally call it innovation pipeline, wherein some of the projects are just sure shot bets, but then they explore these. I mean, Google had this moonshots where they explored really crazy ideas, but at the same time, 95 to 98% of their effort was in just maintaining the search, which is the cash cow. And so what you're suggesting is that's a good way to approach science as well, having a portfolio of research directions so that you're not wedded to any particular one, and you could take more risk on an average.
Exactly. And I think this is the biggest problem, is that scientists are evaluated on the portfolio of one. And so, just, you can think of them as like tiny little businesses with like a single product, and it's just, it's deeply problematic. So, how do you take risks? You hedge your risks, you build a portfolio. I think scientists should do this, not just scientists, humanists as well. I encourage my students, across the academy that I work with and those that I speak to cultivate a range of projects. Then there's two things that happen. One, you have the potential to do something that really is new and really is distinctive to your imaginary, that wouldn't have been achieved, or at least not in the same time frame, without the confluence of like your ideas. So it makes you more important. And second, if you're successful at building a portfolio, then you get known, and your reputation becomes linked with your ability to be a generator of ideas rather than like the staunch defender of ideas or of particular ideas, which allows science to realize that fantasy we were describing earlier. It gets us much closer. It puts us it changes the mindset in a really deep way. So I think there are things individuals can do. There are also things that big funding agencies can do that change that landscape.
Right. So, Professor, we've been talking about scientists, but now talking about the science landscape, some of the people think that a lot of low-hanging fruits have been plucked in science, and scientific productivity in general is coming down. And that's why there is a lot of incremental science and less room for breakthrough innovative science. Do you share that view?
I think there's a possibility that there are diminishing marginal returns to our exploration. So I think it's possible. I certainly do not think it's been proven. And so I'll just give you an example. So Ben Jones, he's an economist at Kellogg's School of Business at Northwestern University. Published a really interesting paper about the death of the Renaissance man and the rise of age. So older people are getting Nobel Prizes, and people are older when they get their first grants and all these things. It turns out that pattern, and he didn't talk about that at all in the paper, but that pattern doesn't hold for first inventions.
Okay.
So people are just as young as they always were with respect to first inventions. What's different about inventions and discoveries is that inventions don't have fields that have like review boards. When you're applying for a patent, it's not like there's an editor from your field who's kind of going, oh, well, you didn't cite these important studies. And no, you have like a patent examiner who's outside that process and who's kind of trying to figure out whatever you did, is there stuff around it, wherever it is in the discovery space on which it impinges that, we should give credit for your discovery. But so I think it's, from my perspective, equally possible that the slowdown that we have is a result of the increased massive connectedness of science. And so we chat more, we're publishing more, we're connected more, we're like seeing others' likes and dislikes, on social media more. We know what everyone wants more. And that's creating enormous pressure, not just to produce innovation, but to produce innovation that's consistent with everybody's expectations. And I think that that almost certainly slows down the generative potential of science. Now, it likely increases replicability for the little science that ends up getting done. So I think a fixation on replicability is deeply problematic for this precise reason. I mean, we don't care about a particular finding in science. We care about the generative engine of science to discover new things that will be relevant to our questions in the future. So I think it's not at all obvious, and I don't believe that the evidence of certain slowdowns or increases in age of scientists suggest that we've plucked out the low-hanging fruits and now we've got to use more energy and climb higher. That's definitely true for the trees that we've climbed. But it may be that there's a whole bunch of trees out there that we just haven't climbed that have low-hanging fruit on it, that are sitting between disciplines.
Yeah.
That are,
Yeah. And I mean, generally, we have more scientists now than ever in history. So, one should naively expect that we should have more breakthroughs like general theory of relativity, quantum mechanics, evolution, natural selection, and so on. But it's just that in popular psyche, all the great scientific theories have been in the past. And either it's because we are innovating so much and there's so many new things happening that you don't get fixated, or it's, I don't know, it just feels like...
I think there are constraints. And some of those constraints are scientific, when we have the general theory of relativity or whatever, this is like a very nice summary of a wide range of complex facts in the world and complex measurements that are generated in the world. And so there's a scientific and a technological aspect to that, right? And both of those constrain the likelihood that we'll discover new things in the future. So the scientific aspect is, there may be simply other things that, this captures a lot, and there's like other little things out there that we have yet to discover, but we've discovered most of the big coarse-grained phenomena. That's the scientific perspective. That's not my hypothesis. It could be true, but it's not my hypothesis. The other is the technological constraint, which is that once you have a theory that works, when I say works, I mean it produces answers that look approximately correct, or that it's useful in a number of activities, or enough people use it, that you have to use it in that field. And so what that means is that like new things, like new observations, have to be consistent with those old mechanisms and machines. Right. So this total fixation, not total, but a widespread fixation in physics, that it's all about integrating all the great forces. Like that's the target. Like we got to integrate these forces. If we find a force that doesn't integrate, then we're going to discount the likelihood. So that's, to me, that doesn't feel scientific. That feels technological. We're basically saying, this component has to interoperate with this component for us to credit this new component as contributing basically to our understanding of the universe. And I think that kind of constraint we can overcome. And I think it's artificial and limiting.
So what you're suggesting is we've put high barriers to entry for new theories by having really high expectations. But is that a bad thing? I mean, one would expect that if general theory of relativity is making GPS work, a new theory that supposedly has to explain something in universe has to be consistent and should make our satellites continue working.
Yeah, I think that it depends on our tolerance for failure. I have a pretty high tolerance for failure, and I'd like to increase that tolerance. So I don't mean that new. So I think yes, I mean that there are theories. So right now it's like we've got a theory that works for some things, it doesn't work for everything. New theories have to be consistent with that theory. All I'm saying is that if we decreased our need for consistency across the space, then we could grow independent theories, which are inconsistent with one another at the present, that would explain more in the total union of phenomena. So I'll give you one example, dark energy and dark matter in physics. So we don't have any measurable evidence that dark energy exists. We don't have any, dark energy existing actually is like, it's one parameter in one equation. Now, dark matter is interesting. Dark matter, we don't have any measurement that suggests that there is something called dark matter, but we do have like 5 sets of equations, all of which point to kind of the same potential, existence of this, of this dark matter. Like when we calculate the amount of the gravity that kind of would occur if we see galaxies exhibiting the kind of, the movements that they exhibit, then, there has to be more matter. And so we assume that matter is dark matter, right? And the same with kind of like expansion for dark energy. There are theories that are alternative theories to explain, why it is that we don't need this stuff that we have no empirical indicators exist. These kind of so-called non-Newtonian theories. These are extremely minority positions in physics. And it's not just because they're crazy. It's because they're perceived as crazy because they don't interoperate with these big, and yet, we have enormous institutional commitments to dark energy and dark matter that we have no empirical evidence exist. Now, I think it's wonderful for us to explore that hypothesis that dark energy and dark matter exist to make things work the way that our theories say that they should work. I just think the pressure that, there are very few great minds who are basically institutionally allowed to work on alternative theories. Basically so part of it's the success of physics makes it difficult for somebody to consider alternatives that would explain really important things that aren't consistent with the great edifice of physics that explains many things. And I think that just puts, that is, do I think that that's a standard that's too high? I do. I think that is going to make it, because what it means is like, we're basically saying, okay, we're only, we've developed this one theory or one big family of theories. Okay. I don't mean to discount the value of these theories. They're enormously powerful. One big family of theories, but they've grown over hundreds of years. And now we're basically going to hold that same standard to a phenomena that's not yet explained, to a theory that needs to explain that phenomena. It needs to be as worked out and as robust and as interoperable with like this enormous edifice of assumptions and calculations that works across all these different contexts. And I think that kind of single standard and evolving standard, like a standard that means that, like everything that we're going to really consider has to like satisfy the epistemic standards of the high watermarks of our prior work, means it's going to be very difficult. Like, it's like someone is going to have to like work in their basement for like 200 years, before they come up with something that can fill those gaps at a level of epistemic certainty that's akin to the other existing theories that are in place. So I do think it's a problem, to be clear.
But it's fascinating because even the two best theories we have, quantum mechanics and general theory of relativity, they don't agree with each other at the extremes. And if there is an inconsistency there and it's perfectly tolerated, physics grad students study both theories, then what you're suggesting is we should give breathing room to literally startup theories in this space of all theories and not have the same standards, because the established theories, they've evolved, they've literally hundreds of scientists output. And
for hundreds of years. I mean, I think, one thing that is I think that the fixation on the importance of consistency across these theories is deeply problematic. Problematic in the sense that it assumes a kind of mechanistic universe, and not that I don't believe that scientists is, that the natural world is explorable and discoverable. But I have enough of what I'll call a philosophical pragmatist in me that I believe that none of our theories are true. They're good, they're good enough, they're useful, but are they true? Do we have the design? Does our equation, is that generating stuff in the world? No, it's not generating stuff. Stuff is happening in the world. We're approximating it with these theories. So the idea that we can't have mutually inconsistent theories that explain part of this unfolding, actually mechanistic universe, I think, again, limits our ability to explain that universe and predict it.
The thing is, we may be mistaking our models for reality itself. And that's a very high standard because we really don't know whether we've uncovered reality or not.
Yeah, we're approximating reality. Is Newton's theory wrong relative to Einstein's approximation of gravity, for example? At most levels of analysis, no. At some levels of analysis, yes. Is Einstein's wrong at some levels of analysis? I don't know. I think that's the idea, is that these are engineering edifices that are meant to explain and predict. But if we really think of them as the truth themselves, then we cut off the possibility of failure. We don't see science as a constructive activity. And,
Right. So since we have maybe 10 more minutes left, I did want to talk about your paper and your research on success. You've written a paper looking at what contributes to success and failure and where persistence plays a role. So I wanted to end our conversation around general, for lack of a better word, lessons you have for the outside of science on how success is achieved across fields.
Sure. Well, so there's one paper, I guess you may be referring to a Nature paper that we published, yes, not this fall, but the fall before, 2019, which actually is really completely in line with some of the things that we've been talking about. And I would say it both, confirms, but also kind of pushed me to believe in this importance of failure even more. What it shows is that across domains of experience, from social movements to startups to scientists that are pursuing NIH grants, that across all these domains, that a track record of accelerating failures is one of the best ex ante and most consistent ex ante predictors of ultimate success available. Which means that if I'm failing faster and faster, then that is a strong indicator that I will eventually succeed. And I think people have talked about this. The people who've talked about these kinds of intuitions are, folks in Silicon Valley, folks in venture capital, and not in venture capital in general, but in venture capital markets where there is the potential to repeatedly fail and build on those failures. What it means, I think, is that if we're talking about like a diverse portfolio of possibilities in science or in technology, in startup companies, even in social movements, that this ability to kind of to actually scatter and pursue a very different approach ends up. So it turns out one of the things that, as we've explored it, it's not just that you like pursue those things. It's that the first thing you do is often the most different of the things that you do. And so what we find is that people who fail initially with an initial company or initial scientific idea, the next thing they do is less radical. The next thing they do is, so if they're not doing that, they're doing something else. They're kind of like, converging to the mean. They're doing something. They're looking left and right. Oh, I've been corrected. I failed. And so, they like converge to what everyone else is doing. And if they converge to everyone else is doing, there's more competition, A. And B, it takes them longer to do it because it's not what they did before. It's like they're rolling the dice all over again. Whereas if they get out there and they get some traction and they fail, but there's like this potential for them to learn something from the feedback, but as a refining activity in its diversity, then they're the most likely to eventually succeed and eventually make a persistent contribution to the economy, to science, to the landscape of social difference. So I think that my hope, to me, this was very encouraging. I mean, this basically is saying to people, take that shot. And then once you take that shot, don't give up too easily. The investment that you've made in difference, in doing something different, is an investment that, if you refine it, as a function of feedback, has a much higher potential of success than if you just, follow the winds of opinion and kind of identify something that everyone else is doing. So to me, it was encouraging along this line.
So what you're suggesting, just to make sure I've captured this right, is every time you're trying, instead of going in completely random directions, you take something from the attempts and try to use that in the next attempt.
Mm-hmm. Yeah, and I think that the way that leads to success is the fact that initial attempt is often quite different. So that first attempt. Now, if the first attempt was a really conservative attempt that everyone else was attempting, then you wouldn't find this effect, or if you found this effect, it would not be very interesting, or certainly wouldn't bode well for innovation in society. For me, it actually provides me with an enormous amount of hope, and it encourages the Don Quixotes of the world to try and fail and try again, and that increasing rapidity is actually. It's not to say that we can't pursue ideas that will ultimately fail. I hope we do. But it is saying that if you try something, don't like immediately converge to the pack if someone criticizes it. And if you don't, then you're more likely to eventually be perceived as contributing something that's ultimately really new and valuable to the system as a whole. So I think science and entrepreneurship and other places work this way, is that they're skeptical of initial differences, but when proved that those contribute something of value, then they lavish more attention on them than they would have lavished if you just confirmed their expectations. And we find this in other work that we've done in science and technology.
So what you're saying, if one does what everyone else is doing, then by definition, success is not guaranteed because you have competition. So the first attempt has to be different enough, but then iteratively hill climb, incorporating what you've learned to seek good enough high ground where you find success, which is different enough from what everyone else is doing.
Yeah, and then that difference will initially, skeptically regarded will eventually make a real contribution. And that's one of the things we find in our studies of science. I have a paper recently where we looked at just, novel combinations of ideas, which tended to come actually from novel expeditions of scientists and engineers they didn't come from like people with unusual backgrounds or from like unusual teams. They came from teams that were in one area who traveled to another area that had never seen people like them before. And that no one like them had seen places or problems like that before. So I think, it turns out that what's interesting is that model by which we identified like the most surprising discoveries itself, like it could predict, like 98% of next year's discoveries. So almost everything's predictable, but the unpredictability of the things that show up next year is the most predictive of their outsized attention and success. So I think the idea is the system is conservative, but the way to change but the system is responsive to surprise, to novelty. It's initially skeptical, but it is responsive to those things. Those are the things that it lavishes new attention on. And so to kind of keep that in mind in the course of your innovating.
Right. And with enough collective risk taking, we can push system to a higher rate of innovation.
Yeah.
Right. Yeah. So I also want to talk about this research direction you're pursuing on aesthetics of knowledge. What is it and why you're interested in it?
Well, I think, one of the things that we were talking about earlier is the canonization of facts and expectations. A study that we began and studied for a while. So there are many things that we care about which aren't just like, fixing a disease or engineering, better structures, better buckyballs, or better whatever it is that, we're going to build the world out of. And we're interested in origins, like the origin of language, the origin of consciousness, the origin of life, the origin of space, like all these origins questions are kind of the biggest, most haunting questions, but they almost invariably mean that we don't have much data because data comes out of institutions. Like the first writing is in Sumerian, priest texts, like that's when you had stable societies with like an elite class that had, but the same is true for the universe. Like it's not until you have a stable configuration of elements that you actually have traces that can allow you a kind of a telescope on the past. And so for these big questions, systematically, it means that we're really not relying that much on data. So what are we relying on? And in our investigations, what we found is that those fields are much more likely for people to look at other people, to notice, are they at Harvard? What was their background? People who were successful, people are more likely to follow. And there's certain ideas which are common in the air that like if some new idea kind of conforms to these like broad expectations or aesthetics about the way ideas should be in a certain area, then they're more widely appreciated and accepted. And so even though people don't talk about aesthetics or priors of knowledge in this way, they're a force. They're a force, which is to say, if you don't have enough evidence, then you have to rely on something else. And one of the things that you rely on is their form. Their aesthetic. Do they feel right? Do they seem right? And so we're trying to understand these aesthetics. One example, which I think is really powerful, that people often call in the history of science the Foreman thesis, comes out of a very long paper. It's like a book-length paper on the Weimar Republic and the emergence of quantum mechanics. So you've talked a little bit about that. It's a wonderful paper from, I think, 1971. And what it shows, it has this beautiful smoking gun argument where it shows that in the loss of World War I in Weimar Germany, that philosophers were like against causality. That the idea that, kind of like history was something you could move towards, you could achieve, And they were kind of like, we need to get rid of these expectations. These drove the war. These drove our failure. And this kind of philosophical anti-causality was like in the air. Physicists were reading it, thinking about it, and writing it. So there's this smoking gun that they were not only reading that, but also writing, some philosophical responses and treatises against causality. And which, his argument is that put them in a mood, these very same physicists, to consider an anti-causal physical theory, i.e. quantum mechanics. That philosophical mood of that moment actually opened their minds to the possibility of a different kind of a theory, and that it allowed them to accept it. Our aesthetics come not just from like the science itself, but they also come from our environments. Like just what's in America, there's certain things that feel resonant, with like the way things are. That's likely different from, that resonance in India or in some other place at some other time. So for example, today, if we had a deterministic model that's describing something that we fundamentally believe in as stochastic, we'd have like a philosophical problem with it. Whereas in Newton's time, if you had a stochastic model that describes something that, should be run by the church or God or the universe, that like the world was seen as deterministic. You had deterministic theory, there was a deterministic aesthetic. So I think these aesthetics are enormously important lenses through which we see the world. And for us to see further, we need to understand the tint of those lenses.
Yeah. It's fascinating because even in quantum mechanics, there is this debate on how do you even interpret it. There's multiverse, there's Copenhagen interpretation, and then all sorts of flavors. And it's, what I find fascinating is because physicists are the most perhaps, objective folks out there, really grounded in nature, but they debate all the time on how to interpret quantum mechanics. And what you're saying, it boils down to aesthetics.
Well, I think I don't think it boils down to aesthetics, but I think there's no question that aesthetics play a role. There's no question. And so I want to encourage the elevation of the acknowledgement of those aesthetics in our discourses. When people talk about a certain solution as being elegant, what exactly does that mean? I believe that it means that it fits well within our minds. And I don't mean any minds. I mean our particular minds. It embeds well in the space of all the things which are embedded within our minds. And if we want to see farther, then we're going to need to take those things into account. And we're going to have to be prepared to find some ugly things. In fact, this is one thing I'm not going to, I'm totally all about bringing AI, and by AI, I don't mean artificial humanoid intelligence. I mean like building machines that don't share our aesthetics and biases to help us see further, to help us consider things that aren't natural for us. Sometimes there are theories that are really ugly database theories. They're just but they do the best, even profitably the best, even per parameter. And so I think we need to, I think if we really want to discover new things, we're going to have to blow our minds.
Yeah. In fact, this drive to seek beauty in theories, I think that should make us skeptical that the better theories out there should necessarily be ugly, because hopefully universe was not designed for making us perceive things.
I think we need beautiful. To be open. I think we have to be open to the fact that things in the universe that better approximate some aspects of the universe will not feel familiar to us.
Great.
So anyway.
Yeah, this is a fascinating note to end with. Thank you, Professor James Evans. I have a lot of fun talking and learning from you. Thank you so much for your time today.
Well, thank you for your engagement and your thoughts. My pleasure.
Yeah, bye-bye. Take care.
Thank you. Yeah, goodbye, Carlos.